The F-1 is a gas generator cycle rocket engine developed in the United States by Rocketdyne in the late 1950s and used in the Saturn V rocket in the 1960s and early 1970s. 5 F-1 engines were used in the SIC first stage of each Saturn V, which served as the main launch vehicle of the Apollo program. The F-1 remains the most powerful single-combustion chamber liquid-propellant rocket engine ever developed. History. The F-1 was originally developed by Rocketdyne to meet a 1955 U.S. Air Force requirement for a very large rocket engine. The eventual result of that requirement was 2 engines, the E-1 and the much larger F-1. The E-1, although successfully tested in static firing, was quickly seen as a technological dead end, and was abandoned for the larger, more powerful F-1. The Air Force eventually halted development of the F-1 because of a lack of requirement for such a large engine. However, the recently created National Aeronautics and Space Administration appreciated the usefulness of an engine with so much power, and contracted Rocketdyne to complete its development. Test firings of F-1 components had been performed as early as 1957. The first static firing of a full-stage developmental F-1 was performed in March 1959. The first F-1 was delivered to NASA MSFC in October 1963. In December 1964, the F-1 completed flight rating tests. Testing continued at least through 1965. Early development tests revealed serious combustion instability problems which sometimes caused catastrophic failure. Initially, progress on this problem was slow, as it was intermittent and unpredictable. Oscillations of 4 kHz with harmonics to 24 kHz were observed. Eventually, engineers developed a diagnostic technique of detonating small explosive charges outside the combustion chamber, through a tangential tube while the engine was firing. This allowed them to determine exactly how the running chamber responded to variations in pressure, and to determine how to nullify these oscillations. The designers could then quickly experiment with different coaxial fuel injector designs to obtain the one most resistant to instability. These problems were addressed from 1959 through 1961. Eventually, engine combustion was so stable, it would self-damp artificially induced instability within 1/10 of a second. Design. The Rocketdyne developed F-1 engine as the most powerful single-nozzle liquid-fueled rocket engine ever flown. The RD 170 produces 11% more and the RD 171 produces 20% greater thrust using a cluster of 4 combustion chambers and 4 nozzles. The M1 rocket engine was designed to have more thrust, however it was only tested at the component level. The F-1 was a liquid-fueled rocket motor, burning a P1 as fuel, and using liquid oxygen as the oxidizer. A turbo pump was used to inject fuel and oxygen into the combustion chamber. The heart of the engine was the thrust chamber, which mixed and burned the fuel and oxidizer to produce thrust. A domed chamber at the top of the engine served as a manifold supplying liquid oxygen to the injectors, and also served as a mount for the gimbal bearing which transmitted the thrust to the body of the rocket. Below this dome were the injectors, which directed fuel and oxidizer into the thrust chamber in a way designed to promote mixing and combustion. Fuel was supplied to the injectors from a separate manifold. Some of the fuel first traveled in 178 tubes down the length of the thrust chamber which formed approximately the upper half of the exhaust nozzle and back, to cool a nozzle. A gas generator was used to drive a turbine which in turn drove separate fuel and oxygen pumps, each feeding the thrust chamber assembly. The turbine was driven at 5,500 RPMs by the gas generator, producing 55,000 brake horsepower. The fuel pump produced 15,471 US gallons of RP1 per minute while the oxidizer pump delivered 24,811 US gal of liquid oxygen per minute. Environmentally, the turbo pump was required to withstand temperatures ranging from input gas at 1,500 degree Fahrenheit to liquid oxygen at 300 degree Fahrenheit. Structurally, fuel was used to lubricate and cool the turbine bearings. Below the thrust chamber was the nozzle extension, roughly half the length of the engine. This extension increased the expansion ratio of the engine from 10:1 to 16:1. the exhaust from the turbopump was fed into the nozzle extension by a large, tapered manifold. This relatively cool gas formed a film which protected the nozzle extension from the hot, exhaust gas. Each second, a single F-1 burned 5,683 pounds of oxidizer and fuel, 3,945 pounds of liquid oxygen and 1,738 pounds of AP1, generating 1,500,000 pound forces of thrust. This equated to a flow rate of 671.4 US gal per second. 413.5 US gal of LOX and 257.9 US gal of AP1. During their 2.5 minutes of operation, the 5 F-1s propelled the Saturn V vehicle to a height of 42 miles and a speed of 6,164 miles per hour. The combined flow rate of the 5 F-1s in the Saturn V was 3,357 US gal per second, or 28,415 pounds. Each F-1 engine had more thrust than 3 Space Shuttle main engines combined. Designer of the pump for the E-1 per Fahrenheit 1 for Rocketdyne was Ernest A. Lamont. His handwritten original calculations are part of the family archives and available for display. He stated that the design of the rocket engine hinged on the question of whether the pump design was viable. Pre- and post-ignition procedures during static test firing, the kerosene-based AP1 fuel left hydrocarbon deposits and vapors in the engine post-test firing. These had to be removed from the engine to avoid problems during engine handling and future firing, and the solvent trichloroethylene was used to clean the engine's fuel system immediately before and after each test firing. The cleaning procedure involved pumping TCE through the engine's fuel system and letting the solvent overflow for a period ranging from several seconds to 35 minutes, depending upon the engine and the severity of the deposits. For some engines, the engine's gas generator and LOX dome were also flushed with TCE prior to test firing. The F-1 rocket engine had its LOX dome, gas generator, and thrust chamber fuel jacket flushed with TCE during launch preparations. Specifications sources F-1 improvements F-1 thrust and efficiency were improved between Apollo 8 and Apollo 17, which was necessary to meet the increasing payload capacity demands of later Apollo missions. There were small performance variations between engines on a given mission, and variations in average thrust between missions. For Apollo 15, F-1 performance was, thrust 1,553,200 pound forces, burn time, 159 seconds, specific impulse, 264.72 seconds, mixture ratio, 2.2674 seconds. IC total sea level liftoff thrust, 7,766,000 pound forces. Measuring and making comparisons of rocket engine thrust is more complicated than it first appears. Based on actual measurement, the liftoff thrust of Apollo 15 was 7,823,000 pound forces, which equates to an average F-1 thrust of 1,565,000 pound forces significantly more than the specified value. F-1A after Apollo During the 1960s, Rocketdyne undertook uprating development of the F-1 resulting in the new engine specification F-1A. While outwardly very similar to the F-1, the F-1A produced a larger thrust of about 1,800,000 pound forces in tests, and would have been used on future Saturn V vehicles in the post-Apollo era. However, the Saturn V production line was closed prior to the end of Project Apollo and no F-1A engine flew on a launch vehicle. There were proposals to use 8 F-1 engines on the first stage of the Nova rocket. Numerous proposals have been made from the 1970s on to develop new expendable boosters based around the F-1 engine design. These include the Saturn Shuttle, and one in 2013. As of 2013, none has proceeded beyond the initial study phase. The F-1 is the largest, highest thrust single-chamber, single-nozzle liquid fuel engine flown. The Rode 170 and a D-171 from the Soviet Union use a cluster of 4 separate combustion chambers and nozzles, giving the appearance of 4 engines. However, the combustion chambers are all driven by a single turbopump. the assembly produces around 20% more thrust than the F-1, the highest thrust liquid fuel engines ever flown. Larger solid fuel engines exist, such as the Space Shuttle solid rocket booster with a sea-level liftoff thrust of 2,800,000 pound-forces apiece. F-1B booster. As part of the Space Launch System program, NASA had been running the Advanced Booster competition, which was scheduled to end with the selection of a winning booster configuration in 2015. In 2012, Pratt & Whitney Rocketdyne, PWR, proposed using a derivative of the F-1 engine in the competition as a liquid rocket booster. In 2013, engineers at the Marshall Space Flight Center began tests with an original F-1, serial number F-6049, which was removed from Apollo 11 due to a glitch. The engine was never used, and for many years it was at the Smithsonian Institution. The tests are designed to refamiliarize NASA with the design and propellants of the F-1 in anticipation of using an evolved version of the engine in future deep space flight applications. Pratt & Whitney, Rocketdyne, and Dynetics, Incorporated presented a competitor known as Pirios in NASA's Advanced Booster Program, which aims to find a more powerful successor to the 5-segment Space Shuttle solid rocket boosters intended for early versions of the Space Launch System, using to increased thrust and heavily modified F-1B engines per booster. Due to the engine's potential advantage in specific impulse, if this F-1B configuration were integrated with the SLS Block II, the vehicle could deliver 150 metric tons to low Earth orbit, while 113 metric tons is what is regarded as achievable with the currently planned solid boosters combined with a 4-engine or S-25 core stage. The F-1B engine has a design goal to be at least as powerful as the unflight-tested F-1A, while also being more cost-effective. The design incorporates a greatly simplified combustion chamber, a reduced number of engine parts, and the removal of the F-1 exhaust recycling system, including the turbopump exhaust mid-nozzle and the curtain cooling manifold. The reduction in parts costs is aided by using selective laser melting in the 3D printing of metallic parts. The resulting F-1B engine is intended to produce 1,800,000 pound-forces of thrust at sea level, a 15% increase over the approximate 1,550,000 pound-forces of thrust that the mature Apollo 15 F-1 engines produced. Locations of F-1 engines. 65 F-1 engines were launched aboard 13 Saturn Vs, and each first stage landed in the Atlantic Ocean after about 2.5 minutes of flight. 10 of these followed approximately the same flight azimuth of 72 degrees, but Apollo 15 and Apollo 17 followed significantly more southerly azimuths. The Skylab launch vehicle flew at a more northerly azimuth to reach a higher inclination orbit. 10 F-1 engines were installed on 2 Saturn Vs that never flew. The first stage from SA-514 is on display at the Johnson Space Center in Houston, and the first stage from SA-515 is on display at the Michoud Assembly Facility in New Orleans. A test engine is on display at the Powerhouse Museum in Sydney, Australia. It was the 25th out of 114 research and development engines built by Rocketdyne, and it was fired 35 times. The engine is on loan to the museum from the Smithsonian's National Air and Space Museum. It is the only F-1 on display outside the United States. Recovery. On March 28, 2012, a team funded by Jeff Bezos, founder of Amazon.com, reported that they had located the F-1 rocket engines from an Apollo mission using sonar equipment. Bezos stated he planned to raise at least one of the engines, which rest at a depth of 14,000 feet, about 400 miles east of Cape Canaveral, Florida. However, the condition of the engines, which had been submerged for more than 40 years, was unknown. NASA Administrator Charles Bolden released a statement congratulating Bezos and his team for their find and wished them success. He also affirmed NASA's position that any recovered artifacts would remain property of the agency, but that they would likely be offered to the Smithsonian Institution and other museums, depending on the number recovered. On March 20, 2013, Bezos announced he had succeeded in bringing parts of an F-1 engine to the surface, and released photographs. Bezos noted, "Many of the original serial numbers are missing or partially missing, which is going to make mission identification difficult. we might see more during restoration. The recovery ship was Seaboard Worker, and had on board a team of specialists organized by Bezos for the recovery effort. On July 19, 2013, Bezos revealed that the serial number of one of the recovered engine is Rocketdyne serial number 2044, the number 5 engine that helped Neil Armstrong, Buzz Aldrin, and Michael Collins to reach the Moon with the Apollo 11 mission. The recovered parts are at the Kansas Cosmosphere and Space Center in Hutchinson for the process of conservation. In August 2014, it was revealed that parts of 2 different F-1 engines were recovered, one from Apollo 11 and one from another Apollo flight, while a photograph of a cleaned-up engine was released. Bezos plans to put the engines on display at various places, including the National Air and Space Museum in Washington, D.C. See also, comparison of orbital rocket engines. References, notes. Bibliography, Apollo 15 press kit, Saturn V launch vehicle, flight evaluation report, AS510, MPS Sat FE71-2, October 28, 1971. External links, E1 at the Encyclopaedia Astronautica, F1 at the Encyclopaedia Astronautica, F1A at the Encyclopaedia Astronautica, NASA SP4206 Stages to Saturn, the official NASA history of the Saturn launch vehicle, F1 engine operating instructions, the Saturn V F1 engine, powering Apollo into history at Springer.com, Remembering the Giants, Apollo rocket propulsion development, 2009, John C. Stennis Space Center. Monograph in Aerospace History No. 45 NASA, How NASA Brought the Monstrous F-1 A Moon Rocket R Engine Back to Life, New F-1B Rocket Engine Upgrades Apollo-era Design with 1.8 mlbs of thrust, MSFC History Office F-1 Fact Sheet.